Welcome back. Okay, things are getting pretty exciting. We are now getting very comfortable with solving second-order linear differential equations, things like the equations that come from F equals ma of a mass on a spring. And today we're going to take a big step to generalize into a much more broad and powerful class of differential equations of higher order. So instead of just having a first or a second derivative in time, now we're going to be able to deal with systems with 3 or 4 or n arbitrarily many derivatives of my state of my system in time. So that's what I mean by higher order ordinary differential equation, is when the differential equation has more time derivatives than just 1 or 2. Okay, so I'll write down kind of the generic system I'm thinking about. So we're thinking about having, dx dt, that's just the first derivative of my state of my system with respect to time. But now we're going to talk about taking the nth derivative of the state of the system with respect to time. Maybe that'll have some coefficient an plus an minus 1, the n minus 1th derivative of x with respect to t n minus 1. I'm just going to write out kind of the generic nth order, higher order ordinary differential equation, and then we'll analyze it. Plus dot 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 plus, and then at some point I have, a2 d squared x dt squared, that's the second derivative with respect to time, plus a1 dx dt, plus a0 x equals 0. So any kind of nth order derivative system you can write like this in terms of these kind of linear coefficients, a1, a0, a2. All of these a's are just numbers, and these are my derivatives of the state of my system with respect to time. Okay, so this is a generic nth order or higher order ordinary differential equation. And up until now, we've only been looking at first order and second order differential equations. And we've guessed solutions like e to the lambda t's, x of t equals e to the lambda t, plugged them in, and figured out what lambda had to be. So we're going to do the exact same thing here. There's shorthand sometimes that I use to write this. So there's an alternative, or you can also write this as there's a shorthand where sometimes you just write, so I would write this an, when I write x kind of in parentheses n, that usually means the nth time derivative, plus an minus 1 times x, the n minus 1th time derivative. It's very hard to erase this without erasing everything. Minus 1 x n minus 1 plus dot 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 plus a2 x double dot plus a1 x dot plus x times a coefficient a0 equals 0. So this is like an alternative shorthand where instead of dx dt, I write x dot. And instead of d squared x dt for the second derivative, I write x double dot. And x triple dot would be the third derivative. And once I stop being able to write, I can't write n dots, so I just say x to the power parentheses n. This just means n time derivatives of x. So these are just two different ways of writing this higher order system. So I'm going to come back to solving this in a minute. But I want to give you just a really simple gut feeling for how you can get these higher order systems. So we know that F equals ma, like Newton's second law, F equals ma, gives me second order systems pretty easily because my acceleration is the second derivative of my position. So if I'm measuring, the position of this mass on a spring as it evolves in time. Let's say there's some rest position here, which I'm going to call x equals 0. So I pull this mass down, I stretch out my spring, I let it go, and it starts oscillating. Okay, that is governed by F equals ma, and a, acceleration, is just x double dot. So really easy to get a second order system, here or here. How do I get these higher derivatives in a way that makes sense? And this is actually really, really simple. So the easiest thing you could do is just add another mass. Okay, so add another spring, add another mass. So now this is, m2 k2, m1, k1, and this will be x1. And let's say that this thing also has a rest position, from here. This will also have a rest position, and this will be x2 of t. So right away, now I have a system of two variables, x1 and x2. And what I'm going to show you now is that you can write this down as a fourth derivative system. Okay? And if I added another mass, I would get a system with 6 derivatives. If I added another mass, I could get a system with 8 derivatives. And kind of interesting, if I actually think about if I think about a little mesh or infinite array of masses on springs, and maybe I could even make it 2D. I could pretty quickly, I could take the limit as the spacing between these becomes arbitrarily small, and as I get arbitrarily many of these things, I can make this kind of a very big array of masses on springs very close together. And this is actually going to be a pretty good model for a tight membrane, like the surface of a drum. Okay, so if you want to play a drum, we will in future lectures in the next weeks from now, we'll model that using the 2D wave equation, okay, the wave equation. But you could think of that as coming from this kind of discrete element method where you write down a bunch of little masses on springs connected to each other and kind of take the limit as they become very, very close and kind of infinitesimal, okay? And in that case, you would get a huge system of ordinary differential equations of many, many, higher order. And that would be approximating a physical system. So I'll come back to that later. No big deal if that kind of went over your head. So let's talk about this system here. So pretty easy to write down the differential equation here. We will have something like mass 1, x1 double dot, plus spring constant 1, x1. Yeah, this thing is also getting a force. Mass 1, I'm looking at my notes and getting befuddled. This mass has a force from this spring, but it also has a force from this spring. So it also has plus K2 x1 minus x2. So kind of when this thing is, if this thing moves up or if this thing moves down, that creates an extension of this spring. So that's x1 minus x2. That equals 0. This is not a physics class. This is a math class. So exactly the details of how I write down the F equals ma is not the important thing. It's what happens next. So that's for this equation. Now for this equation, this mass m2 x2 double dot. I'm assuming no damping here, but you could add damping. Plus k2 times x2 minus x1 equals 0. Similarly, this thing gets pulled up if its displacement is large or if m1's displacement is large in the negative direction, okay? And so this is a system of 2 coupled second order equations. So I'm just going to say that this is a system of 2 coupled second order ODEs. Okay, so they're coupled because the x1 equation depends on x1 and x2, and the x2 equation depends on x1 and x2, so they're coupled, they're intrinsically linked. It's a system because there's 2 of these equations, 2 coupled equations, and each of them is second order because they have second time derivatives. Okay, so this is a system of 2 coupled second order ODEs. Now it would be very easy to write this as a system of 4 coupled first order ODEs. And I'm trying to get you comfortable with the fact that it's easy to kind of go from 2 systems of second order equations to a system of 4 first order equations or a single fourth order equation. Okay, so I'm going to show you all of these. So what you could do is you could introduce a new variable. You could say, I have x1 dot, x2, x2 dot, and you could define, those as the state of a new system. You could literally, create this vector that was x1, v1, x2, v2, and you would write down that system dot equals some big A matrix times, that state, x1, v1, x2, v2. So just like we've done for second order systems, for this second order system and for this one, you can do it for the coupled system. And so actually I would like you to, this is a great homework exercise, so I would like you to kind of maybe pause here and try to transform this system of equations, these two coupled second order equations, into four coupled first order equations. They're first order now because there's only one time derivative, there's only one ddt. So, the x1 double dot is v1 dot, and the x2 double dot is v2 dot. So I've turned these second derivatives into first derivatives by adding new variables. You can do that, okay? So that's one direction. And then the other direction is that you can write this as a single fourth order ODE, meaning I can write this as a single ordinary differential equation in terms of a single variable, but now that single variable is going to have fourth derivatives in that expression. And I'm going to tell you how to do that, and then I'm going to ask you to do that. Okay, so because we're eventually going to want to get a system like this. So how do we do that? So what we're going to do, so the procedure here, maybe I'll erase this and I'll just write it out. The procedure here is we're going to solve the first equation. Let's call this 1, and let's call this 2. We're going to solve the first equation for x2 as a function of all of these x1s, and then we're going to plug that in to the second equation. Okay, so we're going to solve equation 1 for x2 equals some big nasty function of all of the x1, x1 dot, x1 double dot. It's not that nasty of a function. It's just all of this stuff. Then what we're going to do is we're going to take two derivatives of that. So this is step A. Step B is now take two derivatives of x2 double dot. We're literally going to take this function and take two derivatives. So now that's going to be some other function g, and because this had x1 double dots, now it's going to have x1 quadruple dots. So it's going to be in terms of x1, x1 dot, x1 double dot, x1 triple dot, x1 quadruple dot, which I'm going to write as superscript 4. Okay, and now the last part, C, is we're going to plug in to equation 2, into this equation 2. We're going to plug that x2 in here. This expression here, we're also going to plug this expression for x2 in here, and now we're going to have something that's only in terms of x1 and its fourth derivatives. So that will give me a single fourth order ODE. And in general, you can always do this. You can always go from a system of 4 coupled first order equations to a single fourth order. You can always go from a single fourth order to a coupled system to 4 coupled first order, and you can do these intermediates. So these are all completely equivalent systems, and you'll notice that these two second order systems, that multiplies to 4, or a single fourth order, that multiplies to 4, or a system of 4 first order, that multiplies to 4. So those are all the ways you can kind of group this. Maybe I'll just do this. I think what I'm going to do is I'm actually going to show you how to do this and end the video there. And then we're going to revisit these higher order systems in the next video. So I'm actually going to show you how to write this as a fourth order system. Pitter patter. So I'm going to move my x2 over and divide by k2. So I'm going to say x2, if I solve equation 1 for x2, I'm going to say x2 equals everything on the left, which is m1 x1 double dot plus k1 x1 plus k2 x1, and I moved my x2 times k2 over, and I'm going to divide by k2. So this is, 1 over k2, 1 over k2, this is divided by k2. And so this whole thing equals m1, over k2, m1 over k2. Maybe I'll do it right here. This is m1 over k2 x1 double dot plus k1 over k2 x1 dot plus x1. That's what x2 equals. Okay, good. So we've isolated x2. Now what I'm going to do is I'm going to take its second derivative. This isn't that bad, actually, because I just literally add dots to these. That's all, because these are constants out front. m1, k2, k1, and k2 are all constants. So now x2 double dot is just m1 over k2 x1 quadruple dot plus k1 over k2 x1 triple dot plus x1 double dot. And now the last step, this is really easy, is I take this expression for x2 double dot and this expression for x2, which are now only expressed in terms of x1. And I guess I can pick either of these equations, probably this equation, and definitely the second equation, and I plug them in, and I'll have something that's my final answer. So where should I do that? I'll do that in green. This was A, this was B, and now step C. I plug them into this equation, and I'm literally going to have m2 x double dot. So that's m2 times all of this stuff. So m2 m1 over k2 x1 quadruple dot plus m2 k1 over k2 x1 triple dot plus m2 x1 double dot. That's just this term. Plus this stuff now. Okay, plus k2 times x2 is going to be m1 x1 double dot plus k1 x1 dot plus k2 x1, okay, that's this term, minus k2 x1, all of that equals 0. And now I can kind of just group terms and make sure I put all of my x double dots together. And I get something really simple, which is essentially some constant. It doesn't matter what constant this is, m2 m1 over k2 times x1 fourth derivative plus another constant, m2 over k2 x1 triple dot, plus another constant, which is just m1 plus m2 x1 double dot, plus k1 x dot plus k. I think my k2s cancel. Interesting. I think these actually cancel out, unless I messed up something. That might be true. Okay, you can double check my math. I very well could have made a mistake. I don't have notes for this, and I just kind of did this on the fly. Plus 0 times x equals 0. So this is just, it took me about 5 minutes, and I went from this system of two coupled second order equations to a single fourth order equation, just an x1. Okay, and good homework for you would be to do the exact same thing, but now try to write this, isolate the x2 variable, right? This is a fourth order equation in the x2 variable. You would do basically the exact same thing. You would pick an equation, now solve for x1 as a function of x2, take its derivatives and plug it into the other equation. You'll get another system like this, okay? So easy to do this, to go from this system to less variables but higher order, or to go to more variables but lower order. Okay, in the next lecture, we're going to, now that we have this under our belt, now we're going to really start analyzing what do we do with these higher order systems? How do we solve them? How do we analyze them? All right, that's coming up. Thank you.